hope that soon we will have Bogdan also for a course. And so Bogdan, we're happy to have you and good luck. You can start.
Okay, Shahar, thank you very much for the introduction. Good afternoon, everyone. Sorry, I need to, okay, apologize. Okay. So, good everyone, good afternoon, everyone. So, first of all, I need to make a disclosure. I'm not a physicist, right? I'm an electrical engineer, and I've been working in high-tech industry in Dallas, Texas, USA for 20 years, first in Alcatel for 5 years, and then in Texas Instruments in 14 years. So I consider myself an industry guy. About 10 years ago, I moved to academia. So I haven't been there that much as long as in industry. So the reason I mention all of this is because you would expect this breakthrough in quantum computing to be done by a physics person. This is actually not the case. I can draw a similarity to over here to rocket science. So with a rocket science, it takes you can put all the equations, physics equation in a single A4 paper or letter size paper, and that's it. But between that and sending rocket to the moon, it takes tens, hundreds of billions of dollars spent and thousands of engineers working on this. So definitely there is a big gap between science and engineering. Quantum engineering is much tougher than quantum physics. And I believe that nowadays, basically the physicists will need to step aside and let engineers take its role in leading the quantum engineering. Okay, so in 1995, I joined Texas Instruments as an analog designer. I got attracted to TI because of its incredible amount of innovation and pioneering. This is the company that invented the integrated circuits, then DSP, then used DSP to build a calculator, used DSP to do the speak and spell. So I wanted to do something similar. Right, so we had a few things, a few benchmarks in TI. The first was DSP, the second one DLP, Digital Light Processor. So they replaced S for signal with light, and we wanted to make a mark on Texas Instruments with another acronym, which is Digital Radio Processor. So working in a TI was really incredible. You could feel it was a very innovative company. You could feel the spirit of Jack Kilby there in the hallways. Jack Kilby invented integrated circuits in 1958, and he was the second engineer to got the Nobel Prize in physics for his IC invention, because he created a new industry, which is worth trillions of dollars nowadays. So he was not a one-trick type of pony, right? He wanted to show that he can have sustained impact on the technology. So after invention of integrated circuits, he led the team to build the world's first calculator. So at that time, this equipment was badly needed by accountants, students, scientists, and so on. So he built based on his TI technology, and it was very expensive. This was about the cost of a small car, but it was an instant hit. So my first job, as I mentioned, in TI was analog circuit designer. I was working on analog read channel for magnetic recording. There was no RF back then, so pretty much who's who in digital mix signal analog circuit design would work on read channel. This was the biggest kind of area that you can make your impact in, and very quickly you have a magnetic spinning a disk rotating. There is a pickup coil. The signal will be amplified. You are detecting the presence or absence of magnetic domains. It will amplify. It would perform automatic gain control, and then you would do the continuous time filtering. And the beauty of this approach was that the continuous time filtering and the discrete time filtering would basically fit you, take the Lorentzian pulse shape of the magnetic recording signal and fit it in this very nice form, which is called PR4. And it will simplify mathematics. So processing this kind of signal will be extremely difficult, but then if you shape to the PR4 target, you can use the Viterbi detector. So the whole thing was analog, and the output of the Viterbi detector was 1 bit. So we took these ideas later on, and in a few years after, we developed our first digital intensive chip, which I presented at IACC and JSCC, and we pushed the data rate to 750 megasamples per second. So we have created a group which basically developed a, that was 25 years ago, a means of processing almost giga samples per second signals in a very small IC chips. So we took these ideas to the newly created field of RF for wireless communications, and we had lots of fun. As you can see, these are some of the pictures from Halloween. And in year 2000, we acquire a startup company from Israel, from Kfar Saba, which is Butterfly, and the company became Texas Instruments. So there were lots of visits. I've been to Israel many times. They've been to Dallas, Texas also many times. We had lots of meetings, and you can probably recognize some of my friends here during one of these 1 hour meetings. So we joined the forces together, and we created the world's first CMOS fully integrated radio, which was only 10 millimeters square. This was digitally intensive. We call it digital radio processor. Basically, at the heart, we have a digital control oscillator. So the frequency at the output is 2.4 gigahertz, and that frequency is controlled fully digital. There is nothing analog here. There are internals are analog, but like in a flip-flop, the analog nature is constrained to its internals. Then the phase and frequency will be detected by the time to digital converter. And then we close the loop in order to set the proper phase and frequency. And the amplitude modulation will be done, or power modulation will be done by this digital power amplifier. So the whole frequency synthesizer and transmitter was digital. The receiver was not fully digital, but because you cannot put a AND gate directly to the antenna, but it was digitally intensive, halfway between digital and continuous time analog. So as soon as we get our signals, we would strengthen, we would convert to the currents, and currents would be sampled at the RF rate at 2.4 gigahertz, and we would obtain charge packets, and these charge packets will be processed in discrete time signal processing. So the net effect, because I'm an industry guy, we built this 10 millimeter square chip, which was about 1/2 size of the next competitor, about 1/2 cost. So it caught the industry like a wildfire. So these are the chips, these are the phones that we were selling our chips to these manufacturers within a couple of years. Then we took the ideas into the GSM, which was the much tougher standard to address. Probably in some aspects of radio frequency technology, this is probably the toughest spec for the wireless interface. So you can see the architecture is very similar. We have a digital control oscillator, time to digital converter to close the loop, sigma delta dithering, digital power amplifier. This is on the transmitted side, and the discrete time receiver on the receive side. And the whole thing was integrated on a single chip, basically, right? So we can build a module of a very small size, and the net effect was that before this effort, the cost build of materials for cellular phone was $150 US. After that, it was about $10 US. So we basically brought these cellular technologies to the masses. And we did this project together with Nokia. So this is Nokia's digital baseband. This is our digital RF processor. And we had lots of manufacturers to put these chips into their phones. So it went into production in 2006. So these are the cellular phones that we're using our chip, which we did in joint collaboration with TI Israel in Kfar Saba. And this is the largest volume was by Nokia. These are very inexpensive chips. So the emphasis was on cost to make it as cheap as possible. And I need to tell you from my personal experience as an engineer, I went to Thailand, northern Thailand, in a jungle. There was a little town over there, and we went to a local store, and we noticed that the best-selling cellular phones were these Nokia phones. And I had my two boys with me, and I told them, hey, you know, your daddy designs these phones. And if you are an electrical engineer, you know, this is the second most happy moment in your career. Right? Of course, the first most happy moment is to cash your stock options. So I wrote a book, basically took these ideas and submitted for a PhD thesis. So wrote a book based on this. The book was published in 2006, and shortly after the book was translated into Japanese with much nicer figures. So I used this book as a textbook when I moved 10 years ago to TU Delft in the Netherlands. And then 6 years ago when I moved to UCD in Ireland, I used the same book for another graduate level course. So that's just background to basically justify the fact that, hey, I'm not a physicist, and the time for building quantum computer requires now very heavy engineering presence. So what is my intro into these quantum computing? Around 2006, we started looking at single electron devices for the purpose of putting them in the cell phones, because you can do wonderful things. If you can count the number of electrons, you have a very precise clock with an accuracy of about 0.1 ppm, then you can create very tightly controlled current, and building current sources, voltage sources, is extremely difficult in these chips, right? So if you can send these electrons, count these electrons, then you can create extremely precise voltage and current references. So we tried to design it, because at that time Texas Instruments was the leader in process technology development for handheld devices. Intel was the leader for high performance devices, but TI was for low leakage devices. So we tried to build something to show that this is possible. So the name of the game here is to minimize delta C, right? So if I have a capacitor, if I put one electron, one E, this is electronic charge, and if the capacitance C is very small, then my voltage can be quite high, right? So the idea is to bring the capacitance to the attofarad region so that I can get tens and 100 millivolts of change. And if my capacitance is small enough, I can do this operation at room temperature. So that was the crazy idea we had 15 years ago back then. So what we did, we basically have an active area over here, right? Then we have a poly on top of this, and there is a tiny overlap area. So we have active area, right, connected to some potential. We have a poly, and then we have a few, few atomic layer silicon dioxide. So this could be 10 angstrom, just a few atomic layers, right? And we can show this schematically. This is a capacitor, which is non-leaky capacitor, and this is a capacitance with leakage because of the tunneling, right? So we tend to think of electrons as just cannonballs, particles, but in reality, they are wave. They have wave function, and depending on the temperature, depending on the energy, the wave function of an electron can be 1 millimeter or 2 millimeters, right? So it means that the wave of this electron can go through this barrier, and we see things as leakage, right? So the gate leakage is due to this physical effect of tunneling. So we would like to exploit, normally tunneling, gate leakage is a bad thing. We would like to avoid, it's a nuisance, right? Because when we turn on a microprocessor, it burns power, standby power, but we would like to exploit for our single electron quantum operation. So the key here is this equation, right? So E squared divided by 2C, as long as it is 0.1 of kT, that's the thermal noise of that electron, then we can clearly distinguish the effect of a single electron. So if we can build this overlap very small, we should be able to realize this. So we did some efforts. We had a PhD from Berkeley that was helping us, and we did some simulations. We did lots of literature search, for example, paper by Likarev, and this is a simulation for 0.2 attofarad at absolute zero temperature. So you will get this kind of transfer function. This is on the x-axis, we have input voltage over here, and this is number of electrons that are basically jumping in, right? So if you are starting from 0 voltage, there are no electrons, right? And then at 0.2 something volts, 1 electron is jumped, right? At double that voltage, 2 electrons will be there. And we can go opposite side by subtracting the electrons from there. So, so far so good, but at room temperature, we are going to get this kind of function, right? Which is still very distinct. We can still use it for quantum operations as long as the controllable capacitance is a fraction of attofarad, right? So the name of the game is this capacitance, C. It has to be small, less than attofarad, in order to be able to use it at room temperature. So these are some curves, right? So here we have temperature on the x-axis. We have energy on the y-axis. So the kT energy of the electron at low temperature 4 Kelvin, this is the temperature of liquid helium, is this. It's a fraction of electron volts, and at room temperature is just a tiny fraction, 0.03, something like that, of electron volts, right? So the most important slide is here. It basically says that if I have at room temperature, if I have a capacitance of 3 attofarad, right? That will be equivalent to much higher capacitance at a cold temperature, right? So I can go hundreds of times higher capacitance if I want to get the same type of effects operating at high temperature or low temperature, right? So if you can reduce the controllable capacitance, again, this capacitance is to be controllable, then I can operate at a high temperature rather than low temperature. So there's no need of cooling, right? So this is 4 Kelvin. If I still cannot make this kind of capacitance, then what I do, I go to much lower temperatures, such as 10 millikelvin used currently in these dilution refrigerators. So what we did, we built this structure. This is the top view, right? So this is a contact, active area, this is a poly, and this is an overlap. This is a cross section, right? So of interest are these 2 areas in which single electron operation is being done, right? So this side is, let's say, source. This side is drain, right? And we can create a potential energy graph. And if there is enough voltage over here, then there is going to be tunneling of electrons from here to here and from here to here. So in 2006, we used the most advanced process technology available in industry from Texas Instruments, obviously, 45 nanometer CMOS, and we built this tape out to try these ideas. And notice we have many arrays. We have tried different things. You cannot simulate this, first of all. You cannot simulate. It's impossible. There are no SPICE models. So you have to build your own kind of physics models and try to do. And obviously, you will make lots of mistakes, lots of things cannot be predicted. So the idea is to build lots of them. So here is the TEM photograph of this structure, right? So we have contacts, we have this active area, poly in the middle. Let me zoom in. So this is active, this is a poly, and this is, so you can see that there is overlap over here, but there is no overlap here. So this is an example of a failed device, and you can never predict this because you think what you draw in layout is what goes there. That's not the case in advanced process technology. And there is also optical proximity correction, OPC. And there is simply no way of knowing what you're going to actually draw. Right? That's why there are those DRC rules, but if you violate, obviously we are violating the DRC rules, so there is no way of knowing what we are going to do. So the idea is to build thousands of these single electron devices, right? Some of them will be like this. Obviously it's failed because there is no capacitance. Some of them will be like this, because there is too much overlap capacitance, but some of them will have the right amount of capacitance, right? So that's what we did. And we got the devices, we measured. This was a bit disappointing because at room temperature, this is the voltage input, voltage output, right? We would expect these staircase. We didn't see the staircase, but what we saw when you zoom in, this negative resistance area. So definitely a single electron device effect is there, but you know, this is nothing to, again, this was not a research project. This was a, we were thinking about the product, and it was very difficult to convince the management to put lots of people to work on something like this if they were not able to see immediate gratification of volume production. So in 2009, I went to academia. I've never been to academia. As a matter of fact, I've never worked in a research group in a company, always working for a product. So I wanted to try, and the reason I chose TU Delft was because it was ranked 12 in technology. It was in IC circuit design. It was unofficially ranked 1, 2, 3, depending on how do you count. We count the number of ISCC papers. So in 1 year, we had 12 ISCC papers, which was the record, number 1. But most importantly, so this is one half of the engineering building, electrical engineering building. I was on the 18th floor over here. Kofi Makinwa was on the 4th floor. And I said one half because the other half was fab, DMS. So when I was in TI, I could feel I was spoiled because if I needed something, some fib of something done to my chips, I would simply go across the street to the fab and get all the access. Over here, I just simply go to the adjoining building and get everything done while there. So I concentrated on these chips. So this is just 1/3 of the chips which my student did. We, together with Eduardo Charbon, we did this imager chip for SPAT for time of flight lidars. Then when I went to UCD in Dublin about 6 years ago, I got a 6 million grant from Irish government to establish IoT group, circuit design group. And IoT is basically a autonomous self-contained device, which basically contains a processor. It's an intelligent, right? So it needs to do some processor, it's a brain. It senses the environment, so it has a sensor. Some of them can actuate, can do something, open the door, do some movement, and it's autonomous, but it can communicate with other nodes on the network. So it needs to have an antenna and, of course, radio. And there is supposed to be trillions of these devices in a few years, so you cannot imagine replacing batteries. So trillion devices will be something like hundreds, thousands of these devices per person. You cannot imagine replacing the batteries. So each one has to be powered. It needs to extract energy from the environment, such as heat, vibration, electromagnetic, and so on. And I had 20 PhD students working on various blocks to deliver this project and build capability of IC design, academic IC design in Ireland. And these are some of the chips. So we had, for example, in just 1 year, 2016, we had 4 tape outs in 1 year, and each tape out had either 4 or 5 chips. So these are different type of chips in order to realize this kind of vision of IoT. This is 2017 and so on. But about 3 years ago, I stumbled over my former colleague from TI with whom we did this single electron investigation, as I just showed back in 2006. And he told me, hey, remember, we hit a roadblock back in 2006. The best process technology that money could buy was 45 nanometer, and that was not good enough to see quantum operation. It was simply not visible. But guess what? Technology is good enough now, because it's all about this C, the capacitance value. Now capacitance value is much smaller than in the past, so let's revisit this. And he pointed out that actually the internet traffic grows extremely fast. So here we have from 2015 to 2020, which is 2 CMOS nodes. In this 5-year period, the growth of an internet traffic is 18,000. So it's incredible. It's much faster than Moore's law. Right? And why it grows? Well, there are lots of devices, IoT devices, right? These billions, trillions of these devices, they are gathering data, and the data has to be processed by big servers. Images, obviously, there are lots of images. People are watching, sharing video and photo and so on. The regular text is not that much. The enterprise data also has grown, but it's not growing as fast as the other areas. So we look at the market, and you might think, well, with growth, 18,000 growth of internet traffic in the last few years, the PC market will be something to go for. No, it's actually, when you look at the forecast, actual and forecast of PC shipments, laptop shipments, it's actually declining 8% per year. So this is not the business to be in. The business to be in is computing. As you can see, the servers, especially supercomputers, are actually growing about 10% per year. So this is the business we should go in. So we would like to take a slice of this business and enter this via quantum computing. So what is the quantum computing? So this is a very short crash course. So in a traditional computing, the unit of information is bit, the binary bit. It could be 0 or 1. In quantum computing, we also have 0 and 1. We represent this in this so-called block sphere. So this 1 corresponds to here, 0 corresponds to here. But in addition to that, we have all the other possible cases, simply because the qubit, quantum bit, can be in 0 or 1 at the same time, simultaneously, right? And where it is, so for example, this is like a sphere, there is an equator. So if we are somewhere on this equator, then we have equal probability of observing 0 and 1. So it's not that we don't know whether this qubit is 0 or 1, it truly is in this indeterminate state. So this is like a Schrödinger cat, right? The cat is both dead and alive, and unless you observe it, you don't know, and it is indeed in that state until you observe it. Unfortunately, the current quantum computers have to be powered down to 100 millikelvin, which is a very low temperature, requires dilution refrigerators, and these are huge machines that actually require like 2-story housing. So we try to kind of do something to avoid it. And the applications are just enormous, right? You can use this for cryptography. You can do for searching, for data, for image processing. So instead of using FFT, you can do quantum Fourier transform. You can do financial institutions. We recently started talking to MasterCard. They basically said that they have lots of customers who want to optimize their financial transactions, and they are not able to do this because the optimization algorithms require processing power, which basically doesn't exist. So we need to break the current bottleneck of regular classical computing. So we started the company. So the company was with my former colleague in TI, who actually moved to Silicon Valley. So I have my own team in Dublin. We have great academic advisors, and what I'm going to present is basically a combination of academic research and industrial research, and also productization. So my position is a full professor at UCW, University College Dublin, but I'm also a chief scientific officer of Equal1. So I mentioned crash course, very basic in quantum computing. So as I mentioned, in a classical world, we have regular bits. The bit can be in the position of 0 and 1. And in the quantum world, we can be anywhere. There could be a superposition of both bits at the same time. And it's really superposition. It's not that we don't know what it is. Until we observe it, the qubit can be in both places, in both states at the same time. And if we represent electron, for example, position of electron, whether position is at the bottom, top or bottom, the electron is in both places at the same time, right? And we typically use the block sphere representation for that. So, 1 bit in a classical computer doesn't do much, right? So you need to have multiple bits. So on a classical side, we have a classical register. Here is an example of 3 bits. If we have 3 bits, we have 8 of these states. But the power of quantum computer now lies in the so-called qubit register. So adding each qubit into this qubit register basically doubles the computing power. Here we are just adding a bit, so we are linearly increasing the complexity of a regular computer. Here we are doubling the processing power. So if we have a qubit register of 3 qubits, right, then we can have 8 states, and all these states happen at the same time with different probabilities. So you see, there is a possibility to have 1, 1, 1 state, 0, 0, 0, but the most likely state is 1, 1 over here. And this is where the power of quantum operation is. So again, we are exploiting the principle of superposition, right? Meaning that the electron can be in both places at the same time, at the top and at the bottom, two places at the same time. And we have 3 of these electrons, and 3 of these electrons can be entangled with each other. Entanglement is something unique to quantum mechanics. It basically says that one electron state is inseparable from another electron state. So what can you do with this? So this is a single qubit operation. So like in a classical world, we can have an inverter that can simply invert the state of a classical bit. In a quantum world, we can also have an inverter. So we can invert this position over here, which is a classical position. So this is an equivalent to the classical, but we can also change the position when it is entangled. So we are on the equator and we are changing from this position to this position in the, let's say, y-axis. And we can also change in the z-axis by performing the inversion. We can do something which has no equivalence in the classical world. We can do Hadamard gate. So Hadamard gate takes the classical bit and basically rotates, shifts this to the equator. So it means that now we have the input could be classical, right? But the output is a superposition of these two states, where the probability of having 0 and 1 is 50%. So the probability needs to be squared. You can also have two input qubit gate. So in a classical world, we have 2 input XOR gate. This is the truth table, right? The output is 1 if there is a opposite, the inputs are opposite. In the quantum site, we can have also a quantum gate. It's called quantum CNOT, control NOT, or CNOT gate. But one thing, quantum computers, they have to satisfy the thermodynamics, meaning that you don't lose any power. Here, we lose energy. Why do we lose energy? Well, because we are compressing, we are throwing away information, and information is energy, right? So for example, if our output is 1, we don't know if the input is 0, 1 or 1, 0, right? So we are losing the energy. We can go from the output to the input. This is forbidden on the quantum side, right? So the number of inputs has to be the same as the number of outputs, obviously, and it's reversible, right? Means that we have to be able to go to, from knowing the output, we should be able to trace the input. So for example, if the input is 1, 0, we go to 1, 1 as the output, but then feeding that output back to the input, we should go back to the same state, 1, 0. So this is a constraint of quantum gate. So what can we do? We can do, as I mentioned, one big application is image recognition, or MPEG video recognition. It's based on FFT, fast Fourier transform. So if you have a sinusoid, that sinusoid has a certain period or frequency, and the output will show that frequency content here by having this spike over here. So that's the mathematical equation. Now, with a quantum Fourier transform, you can process all the inputs at the same time, right? So the input can be a superposition of all the states, right? And you can process all these states at the same time, right? So it means that you can have increase 2 to the power of n, as n is the number of qubits with your speed up, because using the same hardware, you are running the whole thing in parallel. The math works out fine. We simply, so mathematically we can predict. The field of quantum computation, quantum algorithms is a very well developed field. Mathematically, it all works out quite well. The only problem is that we don't know how to interpret it, right? This 2 to the power of n speed up. So if n is a large number, you know, like 100, 100 on 1,000, then 2 to the power of 1,000, I think, would be like the number of electrons, atoms in the universe, in the entire universe, right? So you can have increased speed up. So there are different theories. Some people claim, and this is actually advocated by David Deutsch, who is the father of modern quantum computing, that we live in a multiverse, meaning that every time there is a decision, the universe splits into two, right? And during this time of the computation, we are harnessing the power of these multi-universes to get the output. So it's not that we are getting this output in our universe, we are getting from other universe. So this is the leading physicist advocates this kind of thing. We probably would never know exactly what it is, and the subject of this philosophical subject is probably a topic for another seminar. So Dr. Shor was the first one to come up with the algorithm, quantum algorithm, would actually showed this speed up, and this was published in '94, and it just exploded the field of quantum computer science. And currently we have something like 200,000, for example, we are working with Qiskit, with IBM, that has quantum operating system called Qiskit, and they say that there are 200,000 registers users for Qiskit, right? So you go log into the machines, and they have emulators, but actually your quantum algorithm can be executed on a real quantum computer. So this is one of the algorithm, and at the core it uses Hadamard gate to prepare the states. The input is just classical, but it prepares the state into 50% superposition, but at the core is quantum Fourier transform. And this is for factorization of prime numbers. It has a huge application in cryptography, for example. So if I have a number 21, right? 21 is 7 times 3. So you can see that the period, the quantum Fourier transform extracts the period, either 7 or 3. And the rest is just classical processing. So you can have a huge speed up. And this is what created this explosive field of quantum computer science. So these are the guts of this quantum Fourier transform, and it uses a bunch of Hadamard gates and rotational gates. We are basically rotating the position on the Bloch sphere. So you've been hearing probably a lot about quantum computing, but it's very difficult to build it. In order to build a quantum computer, you need to satisfy these three conditions, right? So the first condition is that quantum computer is a collection of many two-state quantum mechanical systems, which is called qubits, which they do not decohere, right? And you need to have a method to interact with these qubits in order to generate the universal quantum gates. So you need to have some kind of measurement system. Doing this is extremely difficult because qubits are nanoscopic. They are not microscopic, they are nanoscopic. They are the size of atoms, so they're extremely fragile. And a little bit of disturbance in the environment can basically decohere. They decohere means they lose their quantumness, quantum state. Now, in order to build a practical quantum computer, you need to put many of these qubits together. So when you put many of these together, then you are increasing the number of freedoms, so you're getting closer to the classical system, right? And the classical system basically loses the quantumness. And you need to have extremely fine precision to be able to alter state of these single quantum system at the atomic level. So the qubits currently are error prone. One of the big fields in quantum computing is quantum error correction. So these qubit errors have to be corrected. And if your quantum decoherence is at a certain level, then you can prove with enough quantum error correction, you can actually run these quantum algorithms for any complexity. So let's look at the current state. So the current quantum processors, they are built on Josephson junctions using transmons. We also use the NV center, the nitride vacancy centers in diamonds. Some people use quantum dot arrays for spin qubits. So these are the arrays. There are huge magnets, about 2-3 Tesla magnets. So the quantum state is based on spin up and spin down. And in one of these processors, so the chips are quite small. This is one of those transmons, but they require lots of interface electronics. So the small chip has to be housed in this housing, and you basically put it. So this is one of the smallest quantum machines, right? IBM. You put it in this refrigerator, and then you have to use lots of refrigerator equipment and measurement equipment. So being electrical engineering, I was always interested in how does the schematic of a quantum computer, the current quantum computer that Google's, IBM's of this world have, and this is what I was able to find. So here you have a very small transmon over here. Let me go back a few slides. So this is your transmon, right? And then you have huge microwave type of electronics. So you have isolators because you need to be able to read. So you have a huge magnet, right? Generating 1 to 3 Teslas. You have equipment of extremely high purity because your frequency has to be exact. Let's say frequency is 6 gigahertz and it cannot change more than a few tens of hertz. So it has to be extremely well synchronized. You use the IQ up conversion mixers, some attenuators. And then when you read it, you're reading the spin of an individual individual electron or proton, so the magnetic field change is very small. So you must use extremely high precision equipment to basically provide the gain so that you can read out at the output. So it's huge. And my colleague, Van der Sipien from TU Delft, from QTech in TU Delft, he presented at ISC International Solid State Circuits this keynote, which sounded a bit pessimistic. So he showed this growth of number of qubits versus time. So this is, I would say, equivalent of Moore's law in quantum world. The y-axis is logarithmic, right? So every 5 years, if you will, there is an increase of number of qubits by 10. Right, so we started with 1 qubit, we have 100 qubits, so this is where we kind of are. But these qubits are very error prone. As I mentioned, we need to use error corrections, and the bad thing about error corrections is that for a single useful qubit, we need to have hundreds of ancillary qubits. Right, so the ratio is 100 to 1. So it means that if we have, let's say, using topological qubit, which is error prone, there is no such a qubit, but it exists in theory. If we have 100 of these qubits, then basically we should be able to make any computation we want. We can predict weather, we can do drug synthesis, we can find COVID-19 cure in a matter of seconds, no problem. But these topological qubits don't exist, so we need to have lots of error corrections. So we need to be somewhere over here in the millions of qubits. So if you follow this curve, extrapolate the curves, it will be basically beyond my retirement. Probably even my children will not see this. So my colleague Lieven van der Sipien sounded quite pessimistic, and he said we need to have exponential over exponential. electrons. So this has never happened. So we need to have exponential over exponential, right? So this only happens, for example, when you come up with a radically new paradigm, such as imagine in 1940s, we had the same thing for mainframe computers, right? Using vacuum tubes. So they were pessimistic because we need to have trillions of these vacuum tubes in order to have enough computing power, but vacuum tubes obviously break. So that would not be possible. And then you have invention of transistor and integrated circuits will basically change. So I would say something drastic is needed. So this is a great field. Lots of companies are working on this. Google, Raytheon, Rigetti, Intel, together with University of Delft Technology, and Microsoft is also a new entrant. There are some non-universal quantum computer entrants like D-Wave, which is basically based on quantum annealing, so you can solve certain problems. And our effort is over here, and we are the only one that use the foundry CMOS. So what's the state of these quantum computing? Currently, you have a quantum processor that operates at 15 millikelvin using dilution refrigerators. These refrigerators cost tens of millions of dollars. Then you have classical controller over here operating at room temperature. These are the machines, big machines, so you cannot cool them down, and you need to have some interface. So you are sending these microwave pulses. I showed you lots of microwave components that will put the spin of these electrons in a certain state, up and down. And then you have some control, and then you read very small signal that needs to be amplified. That's the current state. And because of this cooling, it takes this huge equipment. So if you want to have a quantum computer, you can go to dwave.com and spend $15 million to basically buy this. So these are the internals. The chip is very small, but it takes lots of housing to put it together. Lots of cooling issues, right? Because you are going to 15 millikelvin, these metal contracts, so you need to have these loops to prevent it. And these are microwave signals going into the chip. So when you look at the cooling, you have multiple stages, right? So the quantum bits operate at 20 millikelvin, and above that you have 0.6 Kelvin, then you have 4 Kelvin, 60 Kelvin, and so on. So these are multi-stages. In order to reach 20 millikelvin, you need to cool it down for several days. So if there is a mistake, you have like 2 weeks of dead time. And you need to use helium-3 for that. And helium-3 is actually, it's a byproduct of nuclear bombs. So obviously, if we want to work on these ideas, we might have difficulty with Department of Defense. So that's why we wanted to operate at 4 Kelvin. One thing I need to mention is the heat extraction. We are basically pumping into the system about 10 kilowatts of power in order to get only 15 microwatts of heat extraction. So if we have a chip, that chip cannot burn more than 15 microwatts because we will lose this temperature, right? If it burns 0.5 milliwatts, we cannot go below 100 millikelvin. So this is a huge issue with cooling power. So these are some graphs to tell you the cooling capability. So together with my colleague in TU Delft, we decided to change the paradigm, and the paradigm is as follows. So we still have these diamonds, NV centers in diamonds in the quantum processor, but our electronics, the tight electronics, will be operating at 4 Kelvin, which is a temperature of liquid helium. So we are operating it here, right? So the diamond is over here, our electronics is over here, and we can have, according to this one, 2 watts of cooling power, right? So our electronics can burn up to 2 watts of power, and it will be contained over here. So we can control. We can send the qubit spin in a certain state, right? We can read it. We have a bunch of these electronics. So what we did, there were several students involved. This was funded by Intel, and we described this work in these two papers, the ISSC and JSSC, and last time I checked, this was the highest #1 download paper in JSSC last month. So that's the room of experiments. So this is open healing system at 4 Kelvin, right? So this is a helium. It's open vapors. It's not a problem. You will lose this helium, but the price of helium is like a price of good wine. So there shouldn't be a problem in Israel with good wine. And basically you submerge it, and how deep it is, you can control the temperature. So this is our chip. Right? This is the PCB. And one thing we have learned is that even though we use tantalum capacitors, they lose about 10% of the 90% of the capacitance. So basically, you cannot rely on these decoupling capacitors very much. You have to use some other means. And then we have a bunch of the equipment on the room temperature side. So these are the experiments at 160 nanometer CMOS and 40 nanometer CMOS. We obtained this kind of characteristic. We measured at room temperature and 4 Kelvin. And the characteristic changes, and you can see it actually over here, right? So this is the best plot probably. The threshold voltage increases, but the driving strength actually improves, right? So you can exploit it for a digital and analog operation. Some components basically fail, like you have at about 100, below 100 Kelvin, actually it's 77 Kelvin, there is a substrate freeze out. If you have a silicon, there is a freeze out of the carriers. So there is no more generation of electron hole pair. So it basically becomes isolator, but because N-poly and P-active has huge doping, right, it still can work at 4 Kelvin temperature. The BJT devices don't work, right? BJT devices, we use them for band gaps and temperature sensors, and they basically almost fail around 31 Kelvin. But if you exploit digital operation like transistor switches, you can build very high quality oscillators. So this is the oscillator that we have designed for 4 Kelvin operation, and we needed to have at 6 gigahertz carry 1.9 kilohertz of RMS noise. So the phase noise, obviously, the far out phase noise goes with KT, 4 KT, right? So we get huge improvement. And this is the reason that we are able to meet the phase noise specifications. At room temperature, we won't be able to meet the phase noise specification, but at cool temperature, we are because of the KT. The flicker noise is getting worse. It's because of these entrapments. This is still being studied. And we've built this model for the phase noise operation depending on the temperature, right? And then we build amplifiers, LNAs, sensors, and so on, and we started publishing at various conferences. So after this work was done, we had an idea. Why don't we use everything using standard CMOS? Right, we have done lots of experiments with single electron devices, right? If we can create a qubit on standard CMOS that doesn't violate the DRC rules, then we can build millions or even billions of them, right? Just like Intel. Intel can make a single transistor that operates correctly as a switch, and then they can replicate billions in order to create Pentium processors, right? So that was our idea and possible solution to breaking this bottleneck problem with development, scaling up the qubits. So this is our vision, right? We would like to build a single chip, that contains quantum processor over here, right? And on the same silicon die, there are going to be drivers that control the quantum state of these qubits and detectors, right? So the process algorithm runs, and then when we are done, we detect by reading these electrons. And all the processing are going to be done on the same chip, and we only have some kind of UART or USB interface to a quantum computer. And if we cool it down to 4 Kelvin, you can actually go to montanainstruments.com and buy this coffee size cooler at 4 Kelvin. So this is the size of the coffee machine, right? So you put your sample inside, right? It's not a big volume, but it can house a chip. And they even provide you with these RF and electrical controls. You close it and you reduce the temperature to 4 Kelvin, and voila, you can put your, you can build your quantum computer and put it on your desk chip. So quantum computers for the masses, that was our motto. So what do we propose? Well, we propose to avoid using spins because that requires cooling to deep cryogenic temperatures of millikelvin. Here we have a position-based qubit. So we have an electron. An electron is a wave function, right? And if an electron is in this quantum dot, right, then we can control the barrier simply by applying electrical voltage to control the barrier. So the barrier is low. There could be tunneling, so-called Rabi oscillation, and if that electron is in this state, we detect it, and that corresponds to quantum state 0. If it is in this state, it will be quantum state 1. So how does this work? Well, we have this array shift register, and let's say we picked two of these. So the well is shown here as the energy barrier. This is another well, right? And we control the height of this energy barrier by virtue of applying voltage on this, right? So here we are basically taking this and showing over here. We are injecting the electron. Then we are lowering the barrier, so the electron basically repulses itself, right? It basically electron is a wave function, so it's not a particle, and it tries to repel itself. So there is a so-called Rabi oscillation. So if there are no losses, it will keep on oscillating forever. But then at certain point, if the wave function is fully contained in this quantum dot, we raise the, the barrier through the gate. And this operation basically is a transfer operation, is a swap operation. We are swapping the position. So we did lots of, we went back to the physics. We solved the time-independent Schrödinger equation, which is shown over here. And this is a visualization of this, right? So we are showing this position and this position as here and here. So this is a 2D, but it takes lots of computational time to do this. So we say, okay, why don't we just use the line, single dimensional line cross section, because there is no point of going into this Y direction. So when you take cross section, you obtain something like this. And this actually helps a lot with our development. So we get the basis function. So these are the eigen functions, but this is something that we cannot use. But we all know that we can do the use the unitary transformation in order to get to this Vannier type of localized basis. Which is not eigenbasis, but it's derived from eigenbasis, in which the electron on the left will be our 0 logic states, electron on 1 will be our 0 logic states. It is possible, it is allowed because of this unitary transformation. We are going from eigen space to our Vannier space basis. So we started doing these simulations, right? So we have two of these quantum dots here and here, and when we lower the barrier, there is a transition, there is an oscillation, right? So it's basically at a certain point, half of electron is here and half of electron is over here. So let's see how it works, right? So so we are injecting, so this is our starting point. We have two double quantum dots. We have another quantum dot. There is an interaction area where the electrons are allowed to interact. We are injecting an electron here. We are lowering the barrier over here. The electron is tunneling. Then we are closing the barrier. Half of the electron is here, half of the electron is here. And then we are injecting the electron in this site. And now, if we lower the barrier over here, this electron will be entangled with this electron. And this is how we realize the quantum gate operation. So once again, we are injecting electron here. We are lowering the barrier. There is a Rabi oscillation. And at the pi of this rotation, pi 180 degrees, we are raising the barrier. Then we are injecting the electrons in the other structure, the rise structure. Then we lower the barrier, and then these two electrons will be entangled. And the superposition and entanglement will give us this quantum gate operation. So we created a team in Silicon Valley with my former colleagues from TI and in Dublin. And we built, this is the layout of our first chip called Alpha 1. This is the chip, this is the die micrograph. You can see it's flip chipped, wire bonding. And this is one of the, so we put lots of these quantum experiments, 64 of these core. This is one of these layout of one of these quantum experiments. In the middle, there is this quantum area. So this is a quantum area, and the rest is just classical electronics. You see processor, digital processor. DACs, CDACs, detectors, single electron detectors, and so on. So only 0.0001% of the overall area is dedicated to this quantum bit. The rest is just simple electronics, but the connection is very small, right? These are not microscopic, these are nanoscopic dimensions. And this is a TEM micrograph of this structure, right? So here we have quantum dots. These are the gates over here, and this is the interaction area where the two quantum dots electrons in these two quantum dots can interact with each other, right, electrostatically. This is a cross section. So again, this is a TM, and the name of the company comes from entangled quantum aperture logic one-dimensional, meaning that we try to solve these equations, constrain these equations, the wave functions to 1D line, the Shor line. 1D line instead of operating in 2D lines. And these quantum dots are so small that we can get one electron corresponds to about 4 millivolts of voltage change. So this chip, so this is our chip, right? It's a flip chip, right? So this is connected in this PCB. Then we take the PCB and put it on this choke. So this is a cool head. It reaches 4 Kelvin temperature. So we put the entire quantum computer, including Linux server and FPGA and FMC board, in this 12-inch rack over here. So this rack can be movable. It's not very small yet, simply because we wanted to get towards of heat extraction power, and all the electronics is incorporated there. And these are some measurements. So we can see the Rabi oscillation here in this diagram. We also simulate the same structure, and these are results of our quantum simulation. So you can see the Rabi oscillation quite clear. So where we are, basically, when you look at the traditional players, Google, Intel, IBM, Microsoft, Rigetti, and so on, they all operate on semiconductor Josephson junctions, right? They require temperature of 15 millikelvin. We are the only ones that operate at a temperature of liquid helium, which is 100 times higher than there. Now, because we are using CMOS, we can integrate. So our first demonstration had 64 qubits. Second chips, which we are measuring now, has 400 qubits, and the next chip will have 4,000 qubits. So the qubit size is extremely small, as I mentioned, right? It's a tiny, tiny area, whereas the traditional approaches make it much, much larger. So one thing I need to say, because of this temperature and charge qubit operation, the decoherence time is smaller. It's 2 orders of magnitude smaller, but guess what? The decoherence time by itself is not that important. What is important is how many operations can I get within the decoherence time. So traditionally, the decoherence time is longer, 200 microseconds, but it takes 200 nanoseconds for the gate to flip. On our case, we can have 150 picoseconds. So when you divide these two numbers, it's about the same, right? So we decohere faster, but we can make this operation much faster. So in conclusions, so we have successfully designed and manufactured an SoC, quantum SoC, to characterize the charge qubits. The system is built with cryo core, FPGA controlled. Everything is in a 19-inch rack. Everything is fully functional at 3.7 Kelvin. The whole power consumption is only 1.6 milliwatts for a detector, so we are well within 2-watt power budget, and we don't see anything preventing us from putting tens or hundreds of thousand gates within the 2-year horizon. And if we succeed, then we can bring the quantum computing to the masses. And these are our publications. So we have published papers in IEEE Access, in IOP Science, Semiconductor Technology. So these are the journals. Published in optics, special issue in optics, and another IEEE Access. And we also published lots of at conferences. So thank you very much for your attention.
Bogdan, thank you very much. We can take questions by raising hands or writing questions. I see one question already is there. Can you see the questions?
Yeah, I see the question. Why did you sample at 2.4 gigahertz? So this is a direct sampling. It's not direct, it's not subsampling, it's a direct sampling because process technology is fast enough. Remember, in TI, we had access to the best, fastest process technology, and exploiting this discrete time signal processing at the analog charge level, we're able to do it at 2.4 gigahertz because it burns very, very little power, and we avoid all these issues with related to undersampling. So did I answer your question correctly?
Okay, Eran Rotem.
Yeah, why did you use a 22 FDSOI? And what were the challenges? I mean, as far as yield or so, I mean, what accuracy you needed to get?
So as I mentioned, capacitance is the most important thing, and that has to be controllable capacitance. And we did some calculations, very easy calculations, which I included in my presentation. It means that we need to go below 20 nanometer in a bulk process in order to be able to have quantum operation at 4 Kelvin. And we could have gone to FinFETs, but what attracted us to FDSOI is this buried oxide layer. There is a buried oxide layer of thickness of 20 nanometers, and that provides, that separates the defects, and the defects basically can lead to decoherence. So that process basically, so first of all, that process is small enough, allows us to create very tiny structure with small capacitance, and second, it has buried oxide, which helps with isolation and pushing these impurities further away.
Jonathan?
Hi, Bogdan. Thanks for the lecture. I was wondering, so this 64 qubit machine that you've got, is that fully operational as a computation machine? Can you?
Yes, yes. So these are the measurement results. I have some more results. We have much more results, but this is a public presentation, so I could not include it. But we are measuring these. We are measuring these effects. Yeah.
But what I'm asking is like algorithmically, are you able to do similar calculations to the Google machine?
No, it's just beginning. It is just the beginning, right? So we are building. Let me show you more. These structures, right? So for example, this is a 4-qubit structure. This is so here is the gate. Here is a source, here is a drain. So from the drain, we basically remove this raised source drain, meaning that this area is undoped, right? This is a doped area. So we are injecting single electrons basically from this sea of electrons here into this. And then by manipulating the voltages, we are moving electrons at this location, right? And then we do the same thing from here. So these are the quantum gate operations, right? And we have a bunch of them. And what is quantum computer? Universal quantum computer is just a bunch of quantum gates. It's like you can build any classical computer with a NAND gate, right? If you have one NAND gate, that's all you need to build a classical quantum computer. So this is our equivalent NAND gate, quantum NAND gate. Right, we call it C squared NOT. This is a different terminology, but you get the point. And we have a bunch of them, and we can build. We are in the process of building a universal quantum computer. So it's a step by step, right? So first you need to show, okay, it's like invention of transistor, right? We invent the transistor, then we invent the integrated circuits, then we build a NAND gate, then we build flip-flop, then we build memory, then we build the processor. So it's a step-by-step development. And recently we got 4 million euros from Irish government, and we are now applying for about 7 million from European government, and also applying from the US government. I mean, this is a huge engineering effort, right? So as I mentioned before, the rocket science is simple, right? In rocket science, you can put all the equations, rocket science equation on a single sheet of A4 paper, right? But building a rocket requires thousands of engineers, right? So the same thing is going on here, right? We are planning to hire thousands of engineers to build a quantum computer.
Can I be heard?
Yes,
Gadi Eisenstein from Technion. First of all, thank you for this illuminating talk. I have two somewhat unrelated questions. Number one, do you know anything about the fidelity of these qubits, or how equal are they to each other? Because this is a crucial point. It's not the number of qubits that is important, it's their fidelity. And the other question I have is that you seem to have compared or have as a benchmark the superconducting qubits, but you have not mentioned neither the trapped ions nor the photonic qubits, which by now have 1 million qubits, and they're also using CMOS facilities. And I think if you are successful because of the advantages of a CMOS capability, I mean standard high quality CMOS capability, these are going to be the competitors, not the quantum, not the superconducting qubits.
I fully agree, and the word here is commercial, right? I did not show any academic effort because it's too much of this. I'm aware of this, obviously. I fully agree with you.
But there are companies that are doing these things. There's a company in
companies. Yeah, I'm aware these are
the photonic qubits are done only in a company. It's in Silicon Valley, actually.
Yeah.
So people who came from England.
Yes. And
I think, and the trapped ions, the company came out of the University of Maryland. And again, I mean, I think you have a very good chance because once you enter into the CMOS capabilities, you are way ahead of everybody who is not doing it. But the fidelity needs to be addressed. Just the number of qubits means nothing.
Yes. So our fidelity basically can be roughly described as decoherence time divided by gate switch time, right? So you can have something like thousands of these switches per decoherence, right? Here we also have some kind of thousands of these switches. And by the way, we are going through the process. So currently we are measuring something like 100 nanoseconds, right? According to our calculation, the decoherence time should be 1 microseconds. We are measuring 100 nanoseconds, but we are keep on improving our environment, and we keep on increasing. So it's about 1,000 to 1, right? So that's kind of a rule of thumb for the fidelity. Obviously, the fidelity is never going to be as good as, let's say, topological quantum computing, or as you mentioned, trapped ions. I mean, trapped ions definitely are going to win over, but it's extremely difficult to integrate to scale up trapped ions, because these are controlled by lasers, right? And very difficult to go beyond the dozens of trapped ions. Whereas here, if we can create one good quality qubit, just like with Intel processors, we can multiply by billion times, right? Yeah. So the quality of the single qubit is going to be much worse, but we can overcome it by having many of them. You see, so this is our business proposition. This is our new paradigm, to have poor quality qubits, but many of them, to basically compensate for easy decoherence.
Well, I wish you luck. Sounds interesting.
Oh, we definitely need lots of luck.
When you come to Technion, we'll talk more about it.
Okay.
After the crazy Corona time. Thank you. I have to get off, so I really appreciate your talk.
Okay, sure. Thank you very much.
I learned a lot, and I wish you lots of luck.
Thanks. We definitely need a lot of luck.
Thank you, Gary. Tzachi, please, you're next.
Thanks. And I'd like, in some sense, to follow up on the previous questions. You mentioned that this is a step-by-step process, which obviously is true. And my question is whether the remaining steps are simply a matter of difficult engineering, or you see some fundamental unknowns, scalability or otherwise, that may be showstoppers.
No, I don't think there are any showstoppers. The charge qubit, we call them position-based qubits, but in the past they are called charge qubits. They were abandoned about 2 decades. They were quite heavy. Fujisawa, for example, was the leading proponent. And 2 decades ago, they were abandoned, and then we basically picked up. But when you look at why they were abandoned, is because they were using these very exotic technologies, right, from 2 decades ago. And manipulating of these qubits is very difficult. Nowadays, the purity of the material is much better than before because of Moore's law of scaling, right? The companies have invested, like TSMC, Intel, they have invested hundreds of billions of dollars of making these lithography and the purity of CMOS very pristine. So the quality has increased, and basically we are riding on this Moore's law of the development. So the charge qubits are nowadays are much better than in the past, and we don't really see any fundamental limitation. we always are going to have much worse fidelity than in the other approaches. We are very clear about this. We are not hiding it, but everything is integrated. It's next to it, as I mentioned, all the electronics. So right in the middle is our qubit. It's a tiny, tiny area qubit, and all the electronics like detectors, injectors are next to it, right? So we don't have any disturbance from the environment. It's all local. So I think we can exploit this to get very, very good operation in the end.
And the cost of compensating for the lesser quality qubits, is it just a matter of a kind of linear issue? Like if yours are 10 times worse, you need 10 times more, or there's some exponential or polynomial complexity in coming to compensate at the integration level?
No, it's linear, but you can see it's very tiny. This is the electronics that we do this, and it's really powerful. In this chip, we have something like we counted about 100 million gates. So this chip, 3 by 3 in GlobalFoundries, has 100 million gates. So we are basically using millions of these gates to compensate for the imperfections of these qubits.
Okay, and power-wise, it doesn't kill you because these are
no, it just burns milliwatts. And
okay.
we have, at 4 Kelvin, we have watts of power. So we can definitely build millions of these qubits.
I see. So this goes back to the chart you had earlier where you had temperature versus power.
Yeah, exactly.
Gotcha.
Exactly.
Okay, got it.
Exactly. So if you reduce it, obviously we are going to get much better quality of qubit if we go to 15 millikelvin, but then we can only burn 15 microwatts of power. With 15 microwatts, you cannot do anything.
Do you have some notion of the optimal temperature versus power versus how much you can do?
Yeah, I think
you need fewer qubits at a lower temperature.
Yeah, we have, this is the plot, basically. So if you are pumping in 12 kilowatt from the outside, right? This is the temperature, so, and this is the cooling power, right? So it basically at, 17 Kelvin, you can get 10 microwatts, I think, of power. I need to check it, but basically, these are the numbers, right? So at 4 Kelvin, typically you can get 2 watts, right? At 20 millikelvin, you can get 15 microwatts. And at 100 millikelvin, 0.5 milliwatts. That's very little power. You cannot run 100 million transistors at 100 millikelvin because they will burn much more than this. So that's the problem.
Okay, thanks, Tahi. So Liron, please go on.
Hi, this is Liron Gans from NVIDIA. How does your measurement part of the chip scales compared to the quantum part? I mean, if you double the number of qubits, how much more area would the measurements, detectors, and things that you integrate will take?
It's linear. There is going to be a little bit of quantum error correction, right? But it's roughly linear.
Okay, so basically, if you double the number of qubits, you double the area of.
Yeah. So this is a self-contained everything. It has this processor to run all the calibration, detectors, everything. So it's linear.
Okay, thank you.
It's probably less than linear because you can share lots of these electronics. So, for example, one of the structures that we did, if you want to control these gates individually, right, then obviously it's linear. But guess what? You can combine these gates, right? So, for example, you can say I'm injecting an electron here, an electron here, so I can tie this gate with this gate. I can tie this gate and this gate because there is no point of moving this electron first and then this electron second. You can do them at the same time. So you can share lots of electronics. I would say it's sublinear.
Okay, thank you.
Thanks, Liron. And Ron, please go ahead with your question.
Yeah, Alan here from Intel. You mentioned the quantum correction qubits that you need, and I was just wondering, out of these 64 qubits that you have, what is the percentage of the quantum correction bits? And when you scale, do you need to scale the quantum correction linearly, or you need more quantum correction to compensate? I think you showed a graph. It also scales not linearly.
Yeah, so the rule of thumb is you need, for each useful qubit, you need to have like over 100 ancillary qubits for quantum error correction. In these two chips that we have done, so we have two different tape outs already. We don't have any dedicated quantum error corrections. What we do basically, we have these basic building blocks. So we are working on the quantum gates. We are characterizing these quantum gates, and then the next chip we are designing might have some error correction, but we don't have a separate error correction right now.
So when you were talking about the 400 qubits that you mentioned before, that's without the error correction. And yeah. Do you have some kind of an estimate for a real system, how many of these you're going to need out of these, let's say 400?
So the next tape out is going to be, we are planning in a few months, is going to have 4,000 qubits and 4,096 qubits. So about 40, 50 of these qubits will be normal qubits, and the rest will be just for the purpose of correcting ancillary.
Okay, thanks.
Okay, thank you. And Tzachi, you have one more question. Please go ahead with your question.
Yes, a quick question, which is almost at the application level. Is there an I/O bottleneck coming on and off chip for relevant applications, or are they mostly very little I/O and just difficult computing?
So it depends on whether you do error correction, right? I mean, if you do error correction locally, then you don't need to send these signals outside. If you placed some kind of FPGA, a separate chip to do the error correction, obviously you will have I/O bottleneck. I/O bottleneck is one of the big problems because quantum computers are analog computers, right? You need to run these experiments thousands of times, right? So for example, currently the best thing that the quantum computer can do, this is not a joke, but the real thing, is to factorize 21. 21 is equal 7 times 3. Right, so you get you put 21 and as an input, and 3 and 7 will be your output, and you need to run it thousands of times, right? Because each time you get slightly different results because of noise, but it's also because of collapse of the wave function. So if your state is 0.1 for example, then you need to run thousands of these experiments, and then statistically you get 25% bit is qubit 0 and state 0, and 75% state 1. So you need to run lots of these things, So obviously there is going to be lots of I/O bottleneck, and the idea is to put the error correction, quantum error correction, as much as possible in the chip. Okay, but for this reason, we are building the gigabit per second type of communication with a processor.
Okay, so things like factorization, okay, but let's say you can process video fantastically fast, but you need now to get the video in at a fantastic data rate. The ratio of computing to I/O is not always as good as in factorization. Factorization, I give you one number and you work a lot factorized. It's not always the case.
Yeah. Well, so yeah, there's going to be lots of I/O, but we can put lots of memories, right? So you can do compression in the memories. If you have a video, you don't need to send the raw video. You can send the compressed video and then do decompression internally on the chip, right? So it all depends on the application. So having SoC, right, system on chip definitely helps here, because we can do lots of these pre-processing, post-processing on the same die in order to relieve this bottleneck.
Okay, thanks, Tahi. So we are running out of time. So let's take the last question. Ophir, please, your question.
Thank you, Ophir Schwartz from Intel. You put lots of emphasis on how to represent Qubit itself. However, I'm missing something about the actual function that these qubits run through. Where does this function reside, or how does it look like?
Yeah, so Qubit is quantum bit, right? And if you represent in Vernier function, this is a Schrödinger equation, but you make the transformation with a unitary matrix to get the Vernier function, right? You get corresponding to state 0 and corresponding to state 1, right? So this is a single qubit. Then you go, as I mentioned, you go from single qubit to qubit register. So you put 2 of these, 3 of these, 4, and so on. And these wave functions will basically overlap, right? So they will get entangled. So instead of one wave function, I will get collective wave function for these. And then I put these wave functions for things like QFT, quantum Fourier transform, right? Like here, I put the QFT. So these are my quantum registers. Put them in the QFT, and I get the output.
The question is essentially, what is a QFT, or how does it look like in your design?
Oh, QFT is basically, so it uses Shor's algorithm at the core, right? And these are the gates, right? So like you build a computer with gates. So these are the quantum gates, Hadamard gates, and pi2 rotation gates. So these are the inputs, and these are the outputs, right? And basically you propagate this, and that's your output of your QFT that you feed to the next stage. And each one is a qubit. So you need to have a bunch of these qubits, obviously.
I see. Thank you.
Okay, so we still have one more question. Bogdan, is it okay for one last question from your side?
Yes, no problem.
Yeah, okay. Nissan, please, your question. Go ahead. For some reason, he is muted. Nissan, you're muted, so you are allowed to talk now. So please unmute yourself. Okay, so we are experiencing some technical problems with Nissan, so I think we will skip this question. Okay, so if there are no more questions, I want to thank you, Bogdan, for this